This video is on the trigonometric substitution method using sine. That'll be here. And so this particular problem is find the area of a quarter circle of radius 3, which you could do with geometry formulas, but where did that formula come from? So what you do is you can solve this equation for y and get this one. Okay, and the area you're finding is this area right here, this quarter circle right there. Okay, so all that in there. So you do your representative Riemann sum right triangle. It's a left sum picture. And you're going to add those type of rectangles up from 0 to 3. So there is your integral. And substitution is not going to work. Parts isn't going to work. We need another method. The table would work, but how do they get it in the table? So here's your integral here. So what you do is you employ one of two techniques for trigonometric substitution that we're going to see, and we're going to see using the sine or using the tangent. So we're going to use a sine on this one, because when you see in the integral, you see a square root of a squared minus x squared, that kind of form, whether it's in the denominator or the numerator like this. You're going to go for using a sine substitution. So the first thing you do, you draw your right triangle, and since you're going to use a sine, you put your x right here, right there, and then you put the square root part here, okay. And so if you were to do the Pythagorean theorem of this side squared, that's this squared, plus your x squared, that would equal 9 minus x squared plus x squared, which equals 9. So we better have a 3 over here, so that when you use the Pythagorean theorem, you'll have 3 squared, and this will all add up correctly. So that means that the sine of your angle right here, this your angle, is x opposite over adjacent, x over 3. And that's where this idea comes from. Sine theta is x divided by 3, which means that x is 3 sine theta. And you're going to need that 3 to be there, which you'll see in a second. So in other kinds of substitution problems we've seen, you then go ahead and differentiate. This is dx d theta, and you get 3 cosine theta, so dx substitutes out to 3 cosine theta d theta. So then we have an integral that it's a definite integral, so we have to change over the limits also. So when x is 0, sine theta equals 0. So if you're using inverse sine to get the answer, you're going to have 0 here. And when x is 3, theta is going to be pi over 2, because sine theta is 3 over 3. This was 0 over 3. And that was coming from, of course, that sine theta was x over 3. Remember that? Okay, so then we're ready to go ahead and do the substitution. The original integral is right here. So then we sub out the limits. The theta limits are when x was 0, theta is 0. When x was 3, theta was pi over 2. X is 3 sine theta. We saw that. And the dx was 3 cosine theta d theta. So this was the dx, and this in here was the x. Okay, so then we just go ahead and clean that up a little bit. 3 squared sine theta comes down here to 9 sine squared. Factor out the 9. Take the 9 out of the square root to become 3. Square root of 9 is 3. Get it to here. Use a trig identity. 1 minus sine squared is cosine squared. Cosine squared, square root is cosine times cosine, and you get cosine squared. And that's a parts problem, which we've already done in the past. That's a boomerang type. I put it into Wolfram Alpha. I could have looked it up in the table, or we could have done it here, but I didn't feel like doing it in the video again. So that's just going to be this right here. This is your antiderivative. Okay, so then I put that in right here. And we're evaluating from 0 to pi over 2. So then we come down over to here. Come down over to here. And we get this equals over here. So we're over here, and we've come to over here. 9/2 of substituting in pi over 2. Get this. Subtract, substituting in 0 in here. You get these. And so that all adds up to pi over 2. So you have 9/2 pi over 2, 9 pi over 4. And of course, from geometry, you know the area of the quarter circle of radius 3 is pi r squared over 4, which is pi 3 squared over 4, which is 9 pi over 4. So it checks out.